So, in the last class, we have seen how an impulse voltage wave will look like, and now in this class, we will look into the voltage generation. So, first of all, let us see what is the principle of impulse voltage generation. Okay, we already discussed about the impulse waveform or impulse voltage waveform like this, right? It is a wave like this, which is having what a sharp increase or sharp rise in voltage, and then it decays slowly. So this kind of a curve is what is meant by impulse. So how can we develop that? Okay. So basically, as you can see here, there is an exponential increase as well as an exponential decay here. So such a similar characteristics you can see when you are charging or discharging a capacitor. So basically, that is the principle of operation of an impulse generator. Let us say two capacitances like this. Two capacitances are there. We will get into the correct one after discussing this. Two capacitances are there, C1 as well as C2. Okay, and we have a switch which is S. Right. So in this case, if you see, let me say I am applying a potential of V plus or minus V. I am charging this capacitor to C1. Okay. So it is already charged and it is having a potential of V plus or minus V around the capacitance C1. Once it is there, I am going to close the switch. So this switch is closed. Because of that, what will happen? This capacitor C2 will get charged to a potential. Let me call that potential to be V1. Right. So what is the peculiarity of this V1? One thing is quite sure that this potential, this V1 should be definitely what? Less than V. If at all our C1 is equal to C2, in that case what will happen? We can say that the potential across this one, V1 will be what? V by 2. Right. So because that was the original potential that we applied here. So this is the case when you have two capacitances and the capacitance is switched. Okay. Now we are slightly changing the circuit. Now how we are going to change the circuit? A slight variation in the circuit like this. We are going to add resistance also. So first of all, we have our capacitance which we charge to C1 as it is. Then what? Then we have a switch also. Afterwards, I have a resistance R1 which is connected to this switch. Okay, that is my resistance R1. Similarly, across this capacitance, I have another resistance which is R2. This is my C1 and this is my C2. So similar to before, we are applying a potential of plus or minus V volt. Okay, that is charged at first itself. But now we have a switch here, and whenever my switch S is closed, what will happen? When I say my switch S is closed, what will happen? That time, your capacitance C2 will get charged through this R1. Right? That time your capacitance C2 will get charged. Right? So C2 will get charged when your switch is what? In the closed position, and the time constant of which will be determined by what? The resistance. Or we are able to add, before what is happening, if we were only having capacitances C1 and C2, we will not be able to introduce a time delay. That's an ideal circuit. But when we have a resistance in series with the C2 during charging, this is the way it is charging. So that charging time, that will be equal to what? R1 into C2. Right. So there is a charge, the time delay introduced due to this resistance R1. And similarly, when your switch is again, once it is charged to, let me say, some voltage V1, and once it is charged, if I open this switch and this capacitor is getting discharged, in which way? It will be discharged through R2. So again you have a time delay in what? Again when your S is open and what? Your capacitance C2 is discharging. Whenever your capacitance C2 is discharging, in that condition, again you have a time delay of what? R2 C2, right? Or this time constant of that is given by, let me say, dot 2. That will be what? R2 C2, and that will determine how much time it is taking in discharge, right? So once it is charging, you have a potential increase like this. Once it is discharging, what you will have? You will again have a time delay, right? So you are by introducing resistances R1 as well as R2, you are able to introduce what? You are able to introduce time delays. Right, like you have an impulse voltage, and as I already told you, it can be lightning impulse or switching impulse. In both of them, how much time delay you have to introduce, that will be determined by what? R1, R2, and the value of C2. So with this approach, this is the principle of operation of what? Lightning impulse voltage generation. Okay. This is what we are going to particularly look into with different circuit setups. Now, another important aspect I would like to mention here is about this switch on wheel. Right, we should have what? We should have a fast acting switch. Am I right? Because lightning impulse means what? We are talking about 1.2 microseconds or like 20 microseconds, like in microsecond range, and we should have a fast acting switch. When I said S is closed or open, I did not mean a normal mechanical switch. Why? Because a mechanical switch just means what? A mechanical switch that is not applicable here. That is completely wrong. We cannot apply it here because it will introduce more time delay. That is not needed. Then what are we going to use? Anyhow, mechanical switch we cannot use. Then I think you are aware of the power electronic switches like what? Like SCR. Right? SCR means what? Instead of this one, we can have an SCR. Right? That can be operated as a switch by giving electronic signal. So that is okay. But one problem with SCR is that when I am talking about impulse voltage generation, it is about what? Million volts, right? I am talking about kilovolts or very high amount of million volts. In that case, when I use SCR, usually normally the peak inverse voltage of an SCR is around 3 kilovolt only. So when I am talking about several kilovolt, I have to use a series of what? SCRs together, and all those SCRs needs to be connected in series, right? Instead of when acting as a switch, since the peak inverse voltage is only what? 3 kilovolt, I have to connect several SCRs in series, right? I have to connect several SCR in series, so that what? Let me say one is 3 kV. I have hundreds of them, so that I am able to. This is able to withstand 300 kV, right? So in that case, what will happen? All of them need synchronization of switching, right? It is having a trigger unit by which we can use it for switching purpose. But these all need to be synchronized, and that synchronization can cause problem. That synchronization will not be what? All of them will never get the correct synchronization. Understood? All of them will never get the correct synchronization. Due to which what will happen? Due to which we will have what I can say, we will have some attenuation or attenuation in the what? Impulse voltage waveform. Voltage attenuation will happen due to what? Due to the problem in synchronization. So we cannot use mechanical switches, and even though SCRs can do faster switching, still since we have to keep several SCRs in series and they cannot be synchronously switched at a particular instance so correctly, it will create impulse voltage attenuation problems in the waveform. So I cannot use both of them. So what I will be using? Okay. In high voltage engineering, for such a fast switching, as the case it is for impulse voltage, we use a special what I can say switching device, that is nothing but the sphere gap. That is nothing but the sphere gap. Okay, you will have two spheres, and the switching will be determining on what is the breakdown voltage. If you apply some voltage higher than what, you have two spheres, metallic spheres. In between you have air. So where there will be a breakdown voltage that can be determined by the space between them. So whenever we are applying a potential which is above this breakdown voltage, then what? This will act as a conducting path. Okay, once it will act as a conducting path. So such a phenomena will take only, it is of the order of 1 microsecond. How much? It is of the order of 1 microsecond, and that is quite enough for us to make an impulse voltage waveform. So we normally in high voltage engineering, when you think about fast acting switches, then we go for sphere gaps. Not even the highly developed power electronic switches or any mechanical switch, but the sphere gap is such a good solution when you come for impulse voltage waveform generation, where we can use it as a switch. Okay.